I need to take a look at how you go about dividing a square root, but one thing to remember is that whenever you're asked to divide and square roots are involved, the main part of the division process is going to be simplification. So a lot of times the directions, instead of saying divide, even though it will be written in a fractional divisional form, what you're actually going to be looking to do is simplify. Now, with that in mind, we need to know what it takes for a square root to be simplified. Now, first of all, no radicand can have a factor that is a perfect square. For example, and this is the type of thing we've seen before, square root of 50 is considered not simplified because it can be written in factored form as a 25 times 2. 25 is a perfect square. Therefore, for this to be simplified, the 5 has to come out because you take the square root of 25, and that's 5, and the 2 has to stay in. All right. In addition to that, no radicand can contain a fraction. So something like the square root of 1/2 would be considered not simplified just because there's a fraction in there. Now, as far as how we're going to simplify that, that's the type of thing we'll get to in a minute. Now, the next thing we need to do is look at the part 3 of this, and it says no denominator can contain a square root. So in other words, something like 5 over the square root of x is not simplified just because that square root's in the bottom. So again, that's something that we'll look at as far as how we go about doing this simplification. Now, there's a property that we're going to need to use, and that property basically says that the square root of a over b is equal to the square root of a over the square root of b, and we need to stipulate that a has to be greater than or equal to 0, basically meaning a can't be negative, but it could be 0. And we also want to stipulate that b has to be greater than 0. So b has to be strictly positive because we don't want to see a 0 in the bottom of a fraction. Now, what this property is telling us that we can do is take a radical involving a fraction or a fraction of radicals and turn it either from one fraction under one radical into two radicals in a fraction, or if we want to, we could take these two radicals in this fraction and put them back together under one, whichever is the most convenient for us. And we're going to go through some examples here to see when it is convenient to do one of these two things. Now, whenever you're working with a problem of this type, the first advice that I always give people is that if you see an opportunity, let me write that a little bit more neatly, if you see an opportunity to simplify a fraction, you're going to want to do it. For example, I see a fraction underneath this square root, so that is why it's not simplified. So, let's simplify the fraction and see if it helps. 24 over 6 is a 4. That simplifies down. And now, as our number 2 said, we don't have a fraction anymore, but number 1 says no perfect squares underneath the radical, so we have to take the last step, take the square root of 4, and turn that into a 2. So now that's finally simplified. Let's try another one. Let's say we had the square root of 27 over 3. Again, not simplified because we have a fraction underneath. So 27 thirds is 9. Still not simplified because 9 is a perfect square. And there is finally simplified. And to do these, we really haven't used our new property yet. So let's look at one where that property will be needed. If I had the square root of 3 over the square root of 27, I can't reduce in this form, so I need to turn it back into a square root of 3/27. Now that's something I can reduce. This becomes a 1/9. And you notice this one is almost mimicking the last problem. Now that the fraction is reduced, I see perfect squares here. So I'll break it back apart. So I'm actually using the property twice. And I'm just putting it together and breaking it apart whenever it's convenient for me. I put it together here because it was convenient, because it allowed me to reduce. I break it apart here because it's convenient. I can take square roots. And what you'll find is, even though this property is what's telling you you're allowed to do this, you don't actually have to show all this every single time. All right. For example, if I had the square root of 20 over the square root of 80, you really don't have to show putting it together, simplifying, breaking apart. Since they're both under square roots, you can simply say that 20 over 80 reduces to 1 over 4, and you've cut out a couple steps here. Square root of 1 is 1, square root of 4 is 2. So that makes the process a little bit shorter. And it works the same way with variables, as a matter of fact. If we had the square root of a 48 x cubed over a square root of a 2x, I could say 48 over 2 is 24. X cubed over x is x squared, and there's no denominator left because that all canceled out. So I've simplified this considerably, but I'm still not done. Not done because 24 has a perfect square in it. It's a 4 times 6, and then again there's the x squared. So now I'm going to take the square root of 4, which is 2. Can't take the square root of 6, so it stays in. And the square root of x squared is x. So there is your final answer in a simplified form. Now let's look at some larger values and see how this continues to work for us. Let's look at the square root of an 81w to the 5th times z over the square root of 144w z cubed. And again, I don't have to put them all together just to break them back apart. I can start reducing. Now I see here that 81 is a perfect square, so I'm just going to go ahead and take that opportunity and take its square root. 144 is a perfect square, so I'll go ahead and take that opportunity to take its square root. W to the 5th over w is a w to the 4th. And again, it's still inside because I haven't taken a square root yet. I've just simplified. The same with the z's. Z on top, as in first power. Z cubed on the bottom gives me a z square on the bottom. And I start taking square roots again. The 9 was already out. Square root of w to the 4th is w squared. There's the 12. Square root of z squared is z. There's actually one more thing that can be done. Since I didn't simplify these first, once I took the square roots, I had something that needs further simplification. 9/12 is a 3/4, and you've finally simplified that expression. All right, let's go with one more example with larger constants and other variables with exponents. Let's take the square root of a 125 a to the 6th b to the 8th over the square root of a 5 a square b square. Okay? And again, let's see if there's anything that can be simplified here. 125 is not a perfect square, neither is 5, so I'm going to reduce that fraction. 125 divided by 5 is a 25, and it's still underneath the square root because I haven't taken any square roots. A to the 6th over a squared is an a to the 4th. B to the 8th over b squared is a b to the 6th. And no denominator here because everything canceled. Square root of 25 is 5. Square root of the a to the 4th is a square. Square root of the b to the 6th is b cubed. And again, if you haven't noticed yet, an easy way to take a square root with an exponent since this is a 2 on this index here, you can simply say 4 divided by 2 is 2, 6 divided by 2 is 3. That's a quick and easy way to know what power needs to come out. Now on all these problems so far, everything has come out the denominator in a very neat and clean fashion. We need to look at 2 situations next where that might not be the case, where something might get left behind in your denominator, and you need to look at how to get it out. All right, let's go for a very straightforward example. Let's say you've worked a problem and you've been left with 1 over the square root of 7. Kind of stuck there because nothing will factor and cancel, and 7 isn't a perfect square, so you can't actually take the square root. But, as our rules said, no denominator can contain a square root. So I've got to get it out somehow. And with a square root, what you can actually do, well, with any fraction, you can choose to multiply the top and multiply the bottom by anything you want to reduce a fraction or to raise it to higher terms. Well, since 7 isn't a perfect square, I'm going to multiply by another square root of 7. Again, I have to do it top and bottom because I am working with a fraction. Now on top, nothing really wonderful happens, but on the bottom, 7 times 7 becomes 49. So with a perfect square, with a square root, you can multiply by the same value again and create a perfect square. So on top, the square root of 7 stays. On the bottom, the square root of 49 is 7. So your radical is now on top, which is okay. As long as it's out of the denominator, it's considered simplified. Let's try another example similar to that. If we had 5 over the square root of 3, since 3 isn't a perfect square, I will multiply by another square root of 3. On top, I get 5 square roots of 3. On the bottom, I get square root of 9. Again, I've put a perfect square right where I needed it. Square root of 9 is 3, and you're finished. Before you do this, though, something that's important to mention is that the fraction needs to be completely simplified before you do this. In other words, if I had the square root of 5 over the square root of 15, I would want to say 5 into 15 is a 1 over 3. Square root of 1 is 1, and now you've got something on the bottom that you can't take the square root of and you can't get rid of by simplification. And it's only now that I multiply by this other square root of 3 and bring that out. Whoops, square root symbol is gone. Bring that out is the square root of 3 over 3. Now let's do this with a couple variables involved. Let's look at the square root of 6c squared d to the 4th over a 30c squared d to the 5th. And like we've been doing, we reduce everything we can. We're going to have a 6 over 30, leaving a 5 in the denominator. C squared cancels out perfectly, and you've got a d to the 1st left in the denominator. Of course, this is all with a 1 on top. So we break it apart. Square root of 1 over square root of 5d. Square root of 1 is 1, and still we've got this 5d. So everything is simplified, and the radical's still not gone. Now I have to take care of that myself. So I'm going to multiply by, you guessed it, another square root of 5d. On top, I'll have the square root of 5d. On the bottom, I'll have the square root of 25d squared. Square root of 5d stays on top. And square rooting this, now that it's possible, you have a 5d on the bottom. So you basically are going to multiply by whatever it takes to create a perfect square where you need one, and you need it on the bottom, and then you can simplify, finish your simplification. Now, the next thing I need to look at is simplifying a different type of denominator. Now, all the problems we just did, let's back up. All the problems we just did had basically monomials, as in one term, in the denominator. What we're going to look at now are binomials in the denominator. something along the line of 2 over 4 minus the square root of 3. Now, normally, or if we were to do it like we did in our last example, I would just multiply top and bottom by the square root of 3. And that would give us a perfect square. But the problem is when I distribute, I'm going to have 4 square roots of 3 minus the square root of 9. See, here you've got a perfect square where you wanted it, but there you don't. So simply multiplying by the square root of 3 didn't do it this time. And again, the reason that that didn't work is because I have in this denominator a binomial that is 2 terms, not 1. What I'm going to need to multiply by is something called a conjugate. And the pattern for conjugates is if you have an a minus b, and the conjugate of that is a plus b, and vice versa. In other words, if you had an a plus b, you'd multiply by an a minus b. So, following that pattern, I'm going to multiply by 4 plus the square root of 3. Alright, I don't multiply by the exact same thing that was here, like I was doing. Multiply by its opposite, or conjugate, so to speak. Now on top, I'm going to leave it factored for just a minute, because it's the bottom that we have to pay the most attention to. Multiplying two binomials, of course, you have to FOIL. First times first is a 16. Your outer product is a plus 4 square roots of 3. Your inner product is a minus 4 square roots of 3. And your last times last is minus the square root of 9, because that's right here on this multiplication. Here's what we see happening. First of all, 16 is okay in a denominator. Next, the 4 square roots of 3 and the minus 4 square roots of 3 cancel. And we're left with a 16 minus the square root of 9. But 9 is a perfect square. So I've got 2 times 4 plus the square root of 3 over a 16 minus 3, which is a 13. No more radicals in the denominator. So that's the pattern that you have to mimic for this type of problem. Let's look at one more of them, at least one more. Let's look at 6 over 4 minus the square root of y. Instead of a 3 in here, we'll put a y. Change it just a little bit. And actually, let's make this a plus so we can see how the other half of the conjugate works. Instead of multiplying by 4 plus the square root of y, I need to multiply by 4 minus the square root of y. I'm going to do that top and bottom. I'm going to leave the 6 sitting out. I'm never in a hurry to multiply that in. The book might give you a final answer with that multiplied in, but it's really not a big deal. First times first is 16. Outer product is minus 4 square roots of y. Inner product is plus 4 square roots of y. Last times last is minus the square root of y squared. Okay, and again, leaving this alone for the moment. 16, inner and outer cancel. Square root of y squared is y, and there. No more square roots. Alright, let's try one more with a slightly more complicated multiplication involved. If I had 5 square roots of x over 6 minus the square root of x, think about it. Following your conjugate pattern, we're going to multiply on both the top and the bottom by 6 plus the square root of x. Again, the opposite of what we had. On top, we have 5 square roots of x times the 6 plus the square root of x, which we might have to end up multiplying. First times first is a 36. Outer product is plus 6 square roots of x. Inner product is minus 6 square roots of x. Last times last is the minus square root of x squared. As always, this one and that one cancel. This one I can take the square root of, so that's going to be a 36 minus x. And the top, this time, we'll multiply out. 6 times 5 is a 30 square root of x, and then plus 5 square roots of x squared when I distribute the second time. So that's a 30 square root of x plus a 5x over 36 minus x. So that's the basics of dividing with square roots, which as you can see is more simplification than anything.